Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will begin to discuss Kirchoff's circuit laws. So consider the simple circuit again, okay? Remember this is the circuit with a single cell or battery connected to a single resistor. We can ask ourselves the following question, all right? So we know that the current comes from the battery or cell right here and goes this way and goes this way and goes this way all the way through the circuit. So we can ask ourselves, what is the relationship between the current exiting the cell versus the current entering the resistor versus the current in the resistor versus the current exiting the resistor and then re-entering the cell? So how do those five currents compare? And the counterintuitive answer, which we're going to explore a little bit, is that they are, in fact, all exactly the same. Most students, when they first see this, most people, when they first see this example, assume that, there must be some sense in which the current slows down when it hits the resistor in some way. So it comes out strong and sort of re-enters the battery sort of weak. And as it turns out, not only is that not true, it is perfectly not true. That is, the current I4 is exactly the current I1. And so when we label this, we will always label it just with a single current. The value of the current here and here and here and here and here are all the same. Why is this? Well, fundamentally, the explanation is due to what is known as the conservation of charge. And the idea is that charge that enters any point along this simple circuit, any point along the line, must leave it at exactly the same rate, because otherwise, one of the following two things would happen. Either charge would build up at a particular location, right? So let's say it sort of slowed down right here. Well, then charge would begin to build up. And if that happened, then you would have sort of a gradual buildup of or difference in charge, and eventually, actually, the circuit would stop flowing. And that doesn't happen. The circuit just continues. The current goes in and out. Or charge would need to sort of disappear. And if charge disappeared, that would violate the conservation of charge. So fundamentally, we can introduce what is known as Kirchoff's first law, which is related to this direct application of the conservation of charge. So we're applying the conservation of charge to a circuit specifically. And the conservation of charge says that charge can neither be created nor destroyed. And Kirchoff's first law in a circuit, otherwise known as the junction rule, states that the total current into a junction must equal the total current out of that junction. So what goes in must come out is sort of the way I tend to think about it. I prefer to write it mathematically like this. This says the sum of the currents that are going into a junction is equal to the sum of the currents going out of the junction. Okay, what goes in must come out, and that's due to the conservation of charge. The IB will tend to write this kind of equation like this, which just says the sum of all the currents is equal to 0. And what they're doing there is they're just saying, well, the currents in are positive and the currents out are negative. So the sum of I in minus the sum of I out, so to speak, is equal to 0. So these are just two different ways of writing the same thing. This, I think, captures the spirit of the rule. Now, what is a junction? A junction is an intersection of two or more wires. Okay, so here's a classic example here. If you have one wire coming in with current I2 and one wire coming in with I1 to this junction right here, and one current going out, I3, then by Kirchoff's first law, I1 plus I2 is going to be equal to I3. Okay, and that's pretty intuitive to us with this what goes in must come out sort of rule. We can also say, okay, so this is a case where sort of current is joining and adding up. We can also say that current can split. So if we take a look at this example here, I1, the current coming in, reaches this junction and then splits in two. Some of it as I2, some of it as I3. And the amount of the split will depend on other factors in the circuit, but fundamentally we will always know that I1 is equal to I2 plus I3. All right, and this can be used to analyze both more complicated cases and our very first case, the one we started this conversation with. That is, if you consider the currents all along this pathway, both entering a resistor, then in the resistor, and then after it, then you can imagine sort of drawing a junction sort of at any point along the way. But if you draw a junction at an arbitrary place, then the current that goes into that must equal the current coming out. And so therefore, I1 is equal to I2 is equal to I3 as a consequence of the conservation of charge written in the form of Kirchoff's first law. So we can also use this to solve for unknown currents without knowing whether they're going in or whether they're going out. So imagine you had a junction that looked like this. You have 3 amps coming in from here, 4 amps coming in from here, 6 amps going out, and 2 amps going out. Now, just through simple addition, you can probably guess where this is going, but perhaps you didn't know. And so you would sort of guess, I'm going to guess that current is going to come in, but I don't know how much. Then you apply Kirchoff's first law. So if I guess that current is coming in, I'm going to say 3 amps plus 4 amps in plus the current I don't know is equal to 2 amps plus 6 amps going out. You then solve for I and find that that is 1 amp going in. Now what would happen in a more complicated junction if you had guessed the wrong direction? Let's say you guess it's going out. Well, if you follow this through and do the same process, you can solve it out, and what you'll find is that I will be equal, in that case, to negative 1 amp. And so you can interpret that negative as just meaning it's going in the other direction. So if you guess wrong, your answer will just end up being negative. So I would encourage you, when you apply Kirchoff's first law, to record your guess visually. So by drawing perhaps an arrow in one direction or the other on your work.